So again, similar to one of the questions in the last session, excuse me, here we're starting off with a kind of a conceptual question. We're given a chemical equation and we're asked, is this reaction spontaneous? Or the spontaneity of this reaction, is it always non-spontaneous, spontaneous at high T, always spontaneous, spontaneous at low T, or unable to determine? So whenever you're given a problem where it gives you the delta H either directly or indirectly, so here it gives us the delta H indirectly, it says heat is produced from this reaction. And so if heat is produced from the reaction, we know that delta H is negative. Now the reason if we want to determine about spontaneity, what we need is to use this equation, delta G equals delta H minus T delta S. So that's why delta H is important. Again, heat is a product, it's negative delta H. Now we got to look at, get some information about delta S. So is it going to be a positive or negative? And so here, if you notice on the reactant side, we have 4 moles of gas. On the product side, we have 2 moles of gas. So the number of moles of gas decreased going from reactants to products. Therefore, this would be a negative delta S because we're decreasing the moles of gas. Therefore, it's becoming more ordered. Delta S is negative. So here we have delta H is negative, delta S is negative, and now when we put it in to delta G, we have a negative delta H, and this minus T delta S becomes positive. So we have a positive T delta S. And remember, delta G is spontaneous when it's less than 0. So when delta G is less than 0, it's spontaneous. So now looking at this delta G equals negative delta H plus T delta S, you see that at low temperature, and it's relative what we mean by low temperature. At low temperature, delta G would be negative. Because as long as T delta S is smaller than negative delta G, you're always going to get a negative, or excuse me, negative delta H, you're always going to get a negative delta G as an answer. So at low temperature, this reaction is spontaneous. However, at high temperature, delta G would be positive, meaning it would be non-spontaneous. So the answer here, what we can tell about the spontaneity of this reaction is that it's spontaneous at low temperature, because delta G will still be negative. Once delta G becomes positive, it would be non-spontaneous. Now continuing with the same type of reaction, the synthesis of ammonia. Here we're given the equation, the balanced chemical equation. We're given delta H, which is negative 92.2 kilojoules. And the first thing we're asked to do is calculate the delta G nulls in kilojoules per mole. And also on this question, it gives you the molar entropies of the reactants and products. So again, the equation we're going to be using is delta G nulls equals delta H null minus T delta S null. Now you may ask, well, what's the temperature that we're supposed to use? Well, whenever you're given the null sign, the null sign relates to 298 Kelvin, which is the standard temperature for whenever you see delta H, delta G, delta S. Whenever you see that null sign, it's referring to 298 Kelvin. So our temperature here is going to be 298 Kelvin. In order to calculate delta G nulls, we need the delta H null, which is given to us, but we need to calculate the delta S nulls. for this reaction. That's where the molar entropies come from. So delta S of reaction is the sum of the products minus the sum of the reactants. So we set it up. Again, everything has a molar entropy, even elements in their stable form. And so we calculate delta S naught. Here, as we predicted in the previous slide, it was negative. Here it shows you quantitatively that it's negative. Now notice that delta H is in kilojoules, actually kilojoules per mole. And delta S is in joule per mole Kelvin. So best thing to do is, what I like to do is convert delta H to joules, and then we plug it into the delta G equation. So I converted delta H to joules. I solved for delta G, got joules per mole, converted it to kilojoules per mole, and we see it's negative 33.2 kilojoules per mole. Is this reaction spontaneous? Since it's negative, it is spontaneous at 298 Kelvin. So the answer is yes. Now, in the last question, we want to know at what temperature does it go from spontaneous to non-spontaneous, or vice versa. So whenever you're asked a question when it crosses this barrier from spontaneous to non-spontaneous, that means delta G is going to go through 0. So what we want to do is we want to determine at what temperature delta G is 0 given the delta H and delta S that we calculated. So we plug in our delta H again, converted it to joules. Our delta S, we rearrange it to solve for temperature. We get 465.4 Kelvin. At that temperature, delta G is 0. So above this temperature, it would become non-spontaneous. Below this temperature, the reaction would be spontaneous. And if you remember in the previous question, we answered that this reaction would be spontaneous at low temperature. So low temperature is anything less than 465.4 Kelvin. Above this temperature, it's non-spontaneous. So now continuing with the same type of chemical equation. Again, we have the synthesis of ammonia. We want to calculate the K at 298 Kelvin. So before we do the plug and chug, just to let you know a little bit about this. So if delta G is negative, what would be the relationship to K? And so what we have to use is this equation. So delta G naught equals RT ln of K. So if delta G is negative, the exponent of K is going to be greater than, or the K is going to be greater than 1. It's going to have a positive exponent. If delta G is positive, then K is going to be less than 1, meaning it's non-spontaneous, which if K is less than 1, it means there's more reactant than product at equilibrium. So based on the value of delta G, we should, in our mind, have some kind of understanding of what K should be. So here we had calculated delta G to be negative, so our answer should be a K that has a positive exponent. If we do this problem and we see that K has, if we do this problem and we see that K has a negative exponent, that should tell us that we've done something wrong in the math. Because since delta G is negative, K should have a positive exponent. So if you work through this and you get a negative exponent for K, go back and double check your work. So using the delta G calculated in the previous problem, we can set up this equation to solve for K. So again, the R here is 8.314, which is in the units joule per mole Kelvin. So that's why I converted delta G to joules, because our R constant is joule per mole Kelvin. And you see that delta G is negative. This component is negative, so two negatives make a positive. So we get the ln of K equals 13.39. So now you have to do the anti-ln, which is not dirt. It's just a joke. Lawn is grass, anti-ln is dirt. Just a little humor there. Anyways, so here we have to raise each side to the power of e. So when we raise each side to the power of e, we get that K equals 6.5 times 10 to the fifth. And notice that the exponent is greater than 1, just like it should be. So now another application of delta G. Here we have the vaporization of chloroform, CHCl3. Oh no, yes, chloroform. Goes from a liquid to a gaseous state. We have the delta H of vaporization given to us, positive 31.4. We have the delta S of vaporization, 93.6 joules per mole Kelvin. What's the boiling point of chloroform in degrees Celsius? So since we're given delta H and delta S, we're going to be using the delta G equation. And since we want the boiling point of chloroform, remember at the boiling point, we're at equilibrium between the liquid and gaseous state. So we want delta G equal to 0 because that's when it's at equilibrium. So at the boiling point, we're at equilibrium between the liquid phase and the gaseous phase. So we're going to set delta G naught equal to 0, plug in our delta H and delta S. Remember though, you need to convert delta H to joules because delta S is in joules. And by the way, that's probably the most common mistake that is made on questions like this. People forget to convert to the same units. And then we solve for T. And we get T is 335.4 Kelvin, and then we convert it to degrees Celsius. So the boiling point for chloroform is 62.5 degrees Celsius. Now we're getting into a little bit of electrochemistry. And electrochemistry deals with redox reactions. And so one of the things we do with redox reactions is we balance the redox reaction. And it usually indicates what type of medium we're balancing this reaction in. So there are two types of medium. There's the acidic medium, where the reaction takes place in an acidic environment. And then there's a basic medium, where the reaction takes place in a basic environment. So in this question, we're going to look at balancing a redox reaction that occurs in an acidic environment. So the first thing you always need to do in redox reactions is determine what's being oxidized, what's being reduced. So here zinc is a solid. It has a charge of 0. Next we have nitrate. Now we should know from our Gen Chem 1 days that oxygen majority of the time is -2. And if oxygen is -2, nitrogen has to be a +5 so that the overall charge of nitrate is -1. Then we see here zinc is +2 and nitrogen is N2 gas. It's an element, so it's going to have a charge of 0. So we see zinc goes from a 0 to +2, and nitrate goes from +5 to 0. So nitrate is reduced because its oxidation number decreases. Zinc is oxidized because its oxidation number increases. So now we can write the two half reactions for this. So we have the oxidation half reaction where the electrons are products, and we have the reduction half reaction where the electrons are reactants. So notice here that this was N2 and this was NO3. So each nitrogen gains 5 electrons, but since this was N2, I had to balance it on the reactant side. So that's why I put a 2 in front of NO3. Each nitrogen gains 5 electrons, so that's a total of 10 electrons that are transferred. And there are different ways you can approach this. This is the steps I'm going to do is one way, but if you do it in a different order, that's fine as long as we come to the same conclusion. So after you write the half reactions, the next step is to balance the oxygen atoms by adding water. Well, the first reaction doesn't have any oxygen, so it's the same thing. It doesn't change. The second reaction, half reaction, we have a total of 6 oxygens on the reactant side, 0 on the product side. So we need to add 6 water molecules to the product side. That's step 2. So now we have 6 water molecules. After balancing the oxygens atoms, we need to balance the hydrogen atoms. So we balance the hydrogen atoms by adding H pluses to either the products or reactant sides. So again, the first half reaction, the zinc half reaction, there's no oxygen or hydrogen, so it's the same thing. Now notice in the reduction half reaction, we have a total of 12 hydrogen on the product side. So we need to add 12 H plus to the reactant side. And so now the hydrogen are balanced. Also in the half reactions, one thing I want you to note is that the total charge on the reactant side and product side are equal. So here on the zinc, this is a total charge of 0. On the product side, we have a total charge of 0. So -2 and +2 is a total of 0. Now for the other half reaction, on the product side, we have a total charge of 0. On the reactant side, we have 12 H pluses, 2 nitrates, and 10 electrons. So we have an overall charge of 0. So as you're doing these steps, you need to make sure that the overall charge is conserved on both sides of the half reactions. Now we need to balance electrons. So the first half reaction has 2 electrons. The bottom half reaction has 10. So we need to turn the top half reaction into 10 electrons. So we got to multiply the entire equation by 5. So now that we've balanced the electrons, we add both half reactions together. So whatever is the same, we mark off, so the 10 electrons cancel each other out. And what we have left is the balanced chemical equation. So 12H plus 2 NO3 minus gives us 5 plus 5 zinc gives us N2 plus 6H2O plus zinc plus 2. So that's the balanced equation for this reaction.